When we analyse electrical circuits, there are two basic types that we need to think about. One is called series and the other is parallel. Now, the example that I have on the left here is a series circuit, and what we mean by that is that the components are connected one after the other within the same loop, effectively. So in this really very simple series circuit, we just have a single loop all the way around, and each component comes one after the other. In contrast, a parallel circuit, the components, as you can see the way that it's usually drawn, is parallel to each other. They are on separate loops. They're not one after the other. And the effect of this is quite dramatic and does have a significant effect. So if we think about, first of all, the current in each of these cases. So we want to compare the current and the voltage in a series and in a parallel circuit. So if I was to put an ammeter in at this point in the circuit, and I'm going to use a number just to make this a bit simpler. I'm going to just say that there's 3 amps here. If I was to measure the current between the bulbs, it would still be 3 amps. And if I was to measure the current over here after the 3 bulbs, it would still be 3 amps. The current is the same everywhere. The way to think about this is, because current is the rate of flow of charge, it's how much charge there is flowing every single second. So if we go back to our car analogy, if we think of these being 3 cars on the road, on a single straight road, if I have 3 cars at one point, I will still have 3 cars a couple of seconds later. They can't vanish. It's not Back to the Future, it's not the DeLorean, so the cars aren't going to disappear magically. That's just not going to happen. So however many electrons I have at this point, I've got to have the same number over here. So current in a series circuit is the same everywhere, okay? It's conserved. Now in parallel, if I was to do this, so imagine I was to measure the current here and it was to be 3 amps. And what I'm going to do for the purpose of this for a second is I'm going to pretend these 2 bulbs are identical, so they've got the same resistance. If I've got 3 amps here, now when I get to this point, now my cars have a choice. They can either go this way, or they can go this way. Now if these 2 choices are identical, because they have the same resistance, then statistically speaking, I will get 50% go one way, 50% go the other. So I might get 1.5 amps go through this bulb and 1.5 amps go through this bulb. Now if you think of this as like roads, then I would have half my cars go this way, half my cars go this way, and then over here when they join back up, so they would join back up because they'd come back, I'm going to get all my cars back again, so I would then get 3 amps. So you can see by looking at this with current that the current is split between each loop on a parallel circuit, and so current is split because of this idea of choice. But what is true is the current that goes in must be the same as the total current that comes back out again. So even though it will split, it will have to rejoin at some other point in the circuit and restore the original number of cars. Again, they can't vanish from the circuit completely. If we think next about the idea of potential difference or voltage, so potential difference being the energy per unit charge, or the voltage, that's converted from electrical into another form. So that's going to be the voltage across our bulbs. So I need to first of all think about my EMF, my electromotive force. So I'm going to pretend that my power supply here, my battery, is going to provide an EMF or an electromotive force of 10 volts. So that's going to be the voltage or energy into the circuit. That energy is going to be split in a series circuit between my two components. So we used the analogy last time of thinking about this as a running race where I've got to overcome two identical hills. And so I'm going to use half my energy to overcome the first and then half my energy to overcome the second. I'm going to split my energy evenly. So each one of these, if I was to measure the voltage individually with a voltmeter, would be 5 volts. And obviously in total it would be 10. So the EMF is equal to the sum of the potential differences. Now in parallel this is a little bit different. And if I use the car analogy for a second, imagine that this is a motorway and I've got a group of cars. 3 obviously isn't a great number for cars, but I've got a group of cars and we've already said that half of them are going to go one way, half of them are going to go the other. But imagine this was a motorway, slip road, and the road was simply just going to part. It was just going to separate. It's not going to be a dramatic turn or anything like that. The cars generally wouldn't slow down. They would still be going at 70 miles per hour. And that's a good way of thinking about voltage in this case. That half of my cars may have gone this route, but they still have the same energy they did here. Their energy hasn't changed. They're still driving at 70 miles per hour down the motorway, or the electrons are still travelling with the same amount of energy that they effectively picked up from the cell in very sort of simple conception of it. So as the electrons transfer, as they reach the bulb, they will transfer that energy to the bulb and then continue around the circuit. So if I was to measure the voltage or the potential difference across each bulb, instead of it being 5 volts, like in this example, and being split evenly, it would actually be 10 volts for each one. Now, another way of thinking about this is imagine that I've left my house. So this is my rubbish drawing of a house, but I've left my house and I'm going to go on a run. But there's 2 paths that I can take, both with an identical hill that I've got to overcome, and then I'm going to run back to my house. Okay, you can tell why I'm not an art teacher. I apologise. But I've got my run. Now I can only do one of these. I can't do both, right? So if I'm running out of my house here, and obviously there was a 50-50 chance of me going one way or the other. So if I was with a group of friends, maybe half of us would go one way and half of us would go the other. But the amount of energy I have to overcome each of these hills individually is the same as the amount I started with. So I can put all my energy into just overcoming one hill rather than 2. And so this is why we get this idea that the voltage in a parallel circuit is the same on each loop. But what is different is the current is split. So to summarize, in a series circuit, the current is the same everywhere. And that's really, really key. But the voltage or the potential difference is split between the components. In a parallel circuit, the current will split down each of the individual loops depending upon the resistance in each path. And the voltage or the potential difference will be the same for each loop because each loop has the same amount of energy. So let's just think about 2 sort of slightly more difficult examples to sort of bring this together. So imagine, first of all, that I had a parallel circuit and I'm going to use identical bulbs again for a second, but I have 2 on one of my loops, like so. So if my EMF is 10 volts, each loop will have 10 volts. So the voltage across this bulb will be 10 volts. This loop will have 10 volts, but because these 2 bulbs are identical, the voltage would be split between them. So this would get 5 and this would get 5. And that would mean that these bulbs would be dimmer than this one. Now, we've said that these bulbs are identical, but if I just represent the total resistance by the letter R, if the total resistance of this path is R, the total resistance of this path would be 2R, because this has got two identical bulbs, whereas this has only got one, so the resistance here is double. So in terms of my current, what would happen is that as my current is coming through, and if I just use a slightly, I'll use 3 amps again, sorry. So if I use 3 amps, since my resistance here is double the resistance there, I'm going to get double the amount of current coming this way. So my current here is going to be 2 amps. My current here is going to be 1 amp. Because I've got double the resistance here, so I'm going to have half the amount of current there as I am here. Now the way to think about this with my current now is, imagine if we go to the motorway example again, and our motorway splits. So imagine I've got, for argument's sake, 10 cars, which is going to be our 10 amperes. We know that the total number of cars I've got to have might be the same, but imagine that on somewhere down here on the motorway, you get a sign that says long delays ahead on this route. So maybe that's because there is a lorry that's crashed, and there's petrol all over the road, and there's explosions and fire. And if you knew that there was a long delay on this route, right, if you had a choice, you would go, no thank you, and you would go this way. Okay, so if I've got 10 cars, if I know that this route is blocked because there's an awful lot of resistance, what the cars will do is maybe only one of them will go and join this queue, and the other 9 might go over here, especially if this resistance is really big. In the case where the road was closed, none of them would go that way. I mean, they would all go this way. So the same thing happens here, that because this path has a bigger resistance, you can think of it as this path now having 2 hills to overcome rather than 1 hill. Well, the easier option is just to do 1 hill. So most of the current will go this way, and the less of the current will go this way because this has a bigger resistance. Now, if you can understand this lesson, if you can understand the difference between series and parallel circuits, particularly in terms of understanding this little table here, right, current and voltage or potential difference in terms of series and parallel, then you can analyze nearly any circuit that you could be expected to do up to A level. So really make sure that you watch this video again and understand all the concepts in it, because this is probably the most important lesson in electricity.